Hello, my name is Boris Pismenny, and I'll be presenting Disentangling the dual role of NIC receive links. This work was done in collaboration with my advisors, Morrison and Tsafrir. Software and NICs interact via logically cyclic arrays called rings. NIC receive ring entries point to empty MTU-sized buffers, ready to store packets. Multi-call systems employ a receive link per call to scale packet reception capacity. The NIC distributes incoming packets between multiple rings according to a hash on packet headers. In this presentation, we will use the following running example. We have two calls receiving packets, call 1 in blue and call 2 in pink. Each call has a receive link with buffers marked with the corresponding color. These receive links reside in host memory. By default, in 100 gigabit per second NICs, receive links are sized to have 1024 buffers, each large enough to store an MTU-sized packet. As a result, the I/O working set, that is the size of all receive links, is typically greater than the per core last level cache. As a result, high-performance networking applications cannot benefit from optimizations such as DDIO that enable serving NIC DMA from the last level cache. Hence, the performance of these applications will decline. To demonstrate the cause of a large working set, we run an experiment with a synthetic network function that receives packets, accesses memory twice per packet, performs routing, and sends packets out to the wire. We run this network function on all CPU cores, and we load it with 200 gigabits per second using an open-loop load generator. The following figure shows throughput in gigabits per second as a function of link size. We see that links smaller than 256, whose working set fits into the DDIO portion of the last level cache, achieve line rate 200 gigabits per second throughput. Next, we see that links smaller than 1024, which fit in the last level cache but not in DDIO's portion of the last level cache, have up to 15% lower throughput. Finally, with links of 1024 entries or larger, the working set exceeds the last level cache, and all data goes through DRAM, resulting in up to 20% throughput degradation. The takeaway from this is that shrinking receive links may benefit application performance. At first glance, it appears that one may reduce the size of receive links to fit the I/O working set in the last level cache and even in DDIO's portion of the last level cache. This approach works well when traffic is evenly spread across multiple cores. For example, we run DPDK's layer-free forwarding application and measure the maximum throughput without packet loss for various link sizes. And when traffic is spread among multiple cores, we indeed see that we can reach 100 gigabits per second with any link size, including the smallest 64-entry receive link supported by NVIDIA NICs. But reducing the size of receive links isn't always a solution. When traffic is bursty, such as when several flows arrive at a single core, then larger buffers are necessary to absorb these bursts. We repeat the previous experiment using a single core this time. The results show that small links are unable to absorb bursts and therefore result in packet loss and lower no-drop throughput. We can also see that the default 1024 link size works best, and that larger than default links show no benefit. In OSDI 2023, we presented shRing, an alternative receive link architecture that efficiently shares receive link buffers across several cores. By sharing buffers, shRing absorbs bursts directed at a single core, while also fitting the I/O working set within the last level cache in multi-core workloads. Although synchronization on a shared receive link occurs overhead, in shRing, we have shown that it may be preferable to spilling beyond the last level cache. The main problem with shRing is that due to a lack of isolation between calls, when the arrival rate exceeds the service rate, queuing theory dictates that the queue overflows. What this means for shRing is that when packets arrive from the network and one call's arrival rate is greater than its service rate, then the ring fills up with packets waiting to be processed by the overloaded call, resulting in packet loss for all calls sharing the ring. To address this issue with shRing, we had to resort to using heuristics to identify imbalance and to fall back to the baseline. Let's summarize what we've seen so far. On the one hand, it is problematic to reduce ring size as it results in packet loss when traffic is bursting. And on the other hand, it is problematic to share buffers as load imbalance results in packet loss. So, what can we do to address this problem? We claim this problem is caused by an entanglement of two pairs of producer-consumer structures in each receive ring, one for allocation and another for reception. In one, the CPU produces empty buffers for the NIC to consume. In the other, the NIC produces packets for the CPU to consume. Since this is the same NIC and CPU, and most importantly, the same receive ring for both structures, packet processing advances in lockstep. In other words, progress in the packet reception consumer-producer structure necessitates progress in the buffer allocation consumer-producer structure. To solve this problem, we present rxBisect, which disentangles the two producer-consumer structures of receive rings into separate rings. We call one ring AX, which stands for allocation ring, and it consists of empty buffers produced by the CPU and consumed by the NIC. We call the other ring BX, which stands for bisected reception ring, and it contains packets produced by the NIC and consumed by the CPU. Note that the AX ring is always kept full of buffers by the CPU, while the BX ring is typically empty, as the CPU drains it from buffers as soon as possible. The reason BX ring is mostly empty is rooted in queuing theory, which dictates that as long as the service rate exceeds the arrival rate, no long-standing queues are formed. Since the size of the AX ring determines the I/O working set size, we can reduce the I/O working set by shrinking AX rings. And to absorb bursts, we share the buffers of AX rings, while BX rings remain as large as the default ring. The takeaway is that by disentangling the two producer-consumer mechanisms, we address both the I/O working set problem and the single bursty flow problem. The following animation demonstrates how BX rings share AX ring buffers. Suppose we have two calls of the same application, blue and pink, which use rxBisect. Suppose that the blue call suddenly receives a burst of traffic. For instance, because traffic from the other call shifted to it. Now, as packets arrive from the network, the BX ring of the blue call first consumes the buffers of the AX ring of the blue call. Then, when the buffers of the blue call's AX ring run out, it consumes the buffers of the other call's AX ring. In our design, we match the size of BX rings to the sum of all AX rings that provide it with buffers. In this case, two calls with AX rings of two buffers result in BX rings with 4 buffers. When traffic is spread evenly between calls, local per-call buffers are sufficient. In each BX ring consumes buffers from its local AX ring without sharing or borrowing buffers from idle calls. Next, we summarize the differences between rxBisect and shRing. First, as we've seen in the previous slide, shRing can't handle imbalanced loads, as one overloaded call will slow down all other calls sharing a ring. In contrast, in rxBisect, imbalanced load impacts only the overloaded call, while other calls make progress with their AX and BX links unimpeded. Second, shRing necessitates locking in software to synchronize over shared data structures, which increases packet processing latency. In contrast, in rxBisect, calls make progress independently of other calls and with no additional overhead relative to the baseline ring per core model. One benefit of shRing over rxBisect is that it is already available with current hardware, whereas rxBisect necessitates hardware changes. But in our experience, when we started working on shRing, it was also not available. So it's possible that rxBisect will become available in the future. Since rxBisect is currently not available, we implement it using emulation via software NIC. In our system, we have two NUMA nodes, and NICs are connected at NUMA node 0. We run the application's workers on the NUMA node where the NIC is attached. The workers use emulated NIC AX and BX queues that are connected to the emulator, which resides on another NUMA node and hosts non-emulated receivings. Packet buffers are located on the same NUMA node as the NIC, which enables the emulator to capture DDIO effects in the same way non-emulated NICs do. For example, when an AX descriptor is generated by a worker, it's consumed by the emulator and it produces an rxString descriptor on the non-emulated receive ring. Later, when a packet arrives, the NIC writes the packet data to buffers on NUMA node 0, and it writes packet completion metadata to the non-emulated receive ring on NUMA node 1. The emulator converts the completion to a BX link entry, which it writes to the emulated BX link of the corresponding worker call on NUMA node 0, thus completing the emulated NIC's packet processing. We also implemented the baseline private per core ring, which we call priv ring, and shRing using the same emulation techniques. Our emulation of the baseline degrades throughput by up to 12%, thus demonstrating the fidelity of our emulation. To evaluate the performance of rxBisect on a real application, we use a stateful load balancer network function, which rewrites packet headers to spread load among 16 servers. We run the load balancer on all cores and load it with 200 gigabits per second. We compare between the default sized private link per core, which we call priv link, small priv link, which fits in DDIO but will cause loss if traffic is bursty, shRing between 8 cores, and rxBisect between 8 cores. The working set of private links does not fit in DDIO, and hence its throughput is low. Small private links shRing and rxBisect fit in DDIO, hence they reach line rate, improving throughput by 20%. Note that in this experiment, only rxBisect is emulated, and the rest are not emulated. When looking at latency, we see that default private links, which do not reach line rate, have a latency of about 1 millisecond, while small private links, shRing and rxBisect latency is closer to 100 microseconds. The reason for priv link's high latency is that its rxString is full of packets, and so latency consists of the time to process all packets in the ring. In contrast, the reception ring are mostly empty for all other architectures. Last, we look at the performance under processing load imbalance. To that end, we run a synthetic network function on all CPU calls. Each call accesses memory twice per packet except one call, which we designate the target call. On the target call, we vary the number of memory accesses between 0 and 300 per packet. We load our application with 200 gigabits per second of traffic that is spread evenly among all calls except the target call, which receives a very small portion of traffic, only 1%. We plot the throughput of our application as a function of the number of memory accesses on the target call. With private links, the application cannot achieve line rate because its working set is too big, and it performs similarly regardless of the load on the target call. This is expected because 99% of all traffic is being processed by calls other than the target call. In contrast, shRing achieves line rate when the overhead on the target call exceeds 100 memory accesses per second. shRing performance starts dropping. This happens because the slow target call prevents other calls from making progress. Dynamic shRing heuristically identifies the load imbalance and switches to private links instead. rxBisect is the only architecture that achieves line rate at the most imbalanced point, demonstrating that rxBisect provides a small working set by efficiently sharing buffers during load imbalance. In conclusion, the I/O working set imposed by default-sized links is too large to fit in the last-level cache, degrading application performance. Reducing receive ring size cannot address this problem, as links as large as the default are necessary to absorb packet bursts. shRing provides a solution that works only when traffic is balanced, while also requiring software synchronization at all times. We show that by disentangling receive links, we can share receive ring buffers with no software synchronization, thus overcoming the drawbacks of shRing.